Okay, so I will go through 1B. So today's plan is to cover tutorial 6 first, then after that, we will continue to our topic 7. So this is a coupled system that has already been written in proper matrix notation already, right? So once again, is the x prime vector here equals to ax, right? So then this is your matrix A. So now I believe the finding of the eigenvalues and eigenvectors wouldn't be an issue, right? Okay, so you DIY on the eigenvalues and vectors. So maybe you can tell me what do you get for your eigenvalues? You got two eigenvalues, one, right? Then V1 is a eigenvector. Then the generalized eigenvector minus 1, 1. Then you get it, then you use 0 and 1, which means that it's 1, 0. Okay, so this one you will DIY for those who didn't. So after you get your eigenvalues and vectors, right, then it's probably clear that since you have only one eigenvalue, you only manage to get one eigenvector, then the V2 is the generalized one. So which means to say that matrix A will be defective. So A is defective. So when A is defective, you have to use the the solution, the blue box solution, right, for defective matrix A, which is this guy here. So which means to say that because the initial conditions are not given, so therefore the last two matrix you don't really have to multiply out, okay, because there's nothing to multiply. So which means that the general solution, right, will be just this combined to be C1, C2, okay? So therefore you can write like the solution, so the general solution is, so your x of t, which is your x of t, y of t vector. So this guy will be p times e to the jt, right? Times c, which is just a constant vector. Okay? Like c1, c2. So therefore, in this case, your p will be your concatenated eigenvectors and generalized eigenvectors. Then e to the jt will be e to the t. Then the other guy, right? Diagonals, of course, will be e to the t because your lambda is 1. Then the top right must be t lambda t. So which is t e t. Huh? Because you are differentiating with respect to lambda. This is d lambda, no? So it's always having a t here. Yes, it doesn't matter what's lambda. This is always t e lambda t. This is always t lambda t. Is that all right? So therefore, this is your solution form. If you write this down correctly, you will get substantial marks already. So now if you multiply out, you will get your C1 ET. So you might realize that actually the solution, if you want, you can just factorize out the ET out. Okay, e to the t can be factorized out. Because since in this case, all terms have e to the t. Okay, so if you want, you can actually do that to make everything simpler. But I think I just stick it to the current form here. So therefore, you have C1 ET, right, plus C2 TET. Then the second row will clearly be just C2 ET. So that's your multiplication. And then if you multiply by the first matrix, clearly you're going to get this guy plus this guy. So let me just factorize out ET because you have all the ET terms of in all terms. Okay, so if you factorize out ET, that means this guy will be giving you 2 times C1, 2 times C1 plus C2T. Then here you have, let me see. Hey, wait a minute. This should be 2C2. Then this is a plus C2. Okay? Then the second row will clearly just be the first row right here. Okay? Then because you factorize out ET already, so here will be your x of t, y of t. Is that right? Okay. So any other questions in question 1 you want me to go through? The rest all good? C and D and A? Okay, good. So question 2 is about using Duhamels because as you can see all systems here are inhomogeneous. They have a f of t function. Some are constant vectors, some are functional vectors. Any requirements? C, 2C. Somehow the matrix looks familiar. I think it's the same one in the tutorial question, in the lecture, is it? I suspect it's the same one in the lecture. So you DIY for the lambdas and the eigenvectors. What do you get for lambda? Anyone? Anyone have done it? No? I think I have the eigen. I think it's this one, right? Is it this one? 2, 1 minus 1, 4. 1 minus 4. Oh, it's not the same. Okay, that means I don't have. No, nobody has done the eigenvalues and vectors. Okay, then we just quickly go through. So your eigenvalue equation will be lambda square. So the trace here, right, will be minus 6. So plus 6 lambda. Then this guy, the determinant will be minus 7 plus 16, right? Then there's a plus 9. So which means to say that your eigenvalue will be 3. Sorry, minus 3. So lambda 1, 2 equals to minus 3. Okay? So chances are you are going to get the defective matrix A. So therefore, your eigenvector, right, will be A minus lambda I, there's only one lambda, times V1, finding the eigenvector. So therefore, you have 1 minus minus 3, that's 4, minus 4, 4 minus 4. Okay? So then you are going to get the span that is y equals to x. Okay, so 4x minus 4y. So you eventually get y equals to x. So then after that, you can get v1 to be 1, 1. So now you have only one eigenvector. So therefore, now we solve for the generalized eigenvector. Solve it from here. So this guy must be 1, 1 then. So if you take any of the rows, you are going to get dependent rows, as you can see, right? So you get 4 x minus 4y equals to 1, right? So which means that you are going to, let's say, isolate y. Doesn't matter which one you isolate. Let's say if I isolate y, right? Then I'm going to get 4x, or rather 1/4 of 4x minus 1. Agree, yeah? So if I choose x to be 0, conveniently, then my y must be minus 1/4. Okay? That is not nice because there's a 1/4. Okay? So what I'll suggest is that you make the V1 here change to 4, 4. Because y equals to x, right? If you make it 4, 4, then what's going to happen is that if you choose, wait, is that correct? Also cannot, is it? Wait. Oh, I think I should make x 1/4, right? Hold on. Okay. I see where this is going. So you see this is 1. This is 1, like this is not nice. So therefore, I change this to 4, 4. So this is of course on hindsight after you try. Because when this is 4, 4, then this is 4, 4. So this will become 4, 4. But the purpose of this becoming 4, 4 is such that you don't get a nasty looking fraction. You can still work with the fraction. Okay, so this one becomes 4. So you see, if this becomes 4, then after that you don't have the 1/4 already. Right? So this becomes y equals to x minus 1. So that'll be nicer. Is that right? So if that's the case, then you can choose your V2, your generalized eigenvector V2, right, to be 1, 0. You can put 0 minus 1 also can. Okay, but 1, 0 probably is nicer because you don't have a negative. So therefore, the V2 is generalized. This one is generalized. So after that, you can use the Duhamel's principle for generalized for defective matrix A. Okay, so let's go back to our lecture notes. So you can see that the Duhamel's principle, right, is this guy. Where's my defective? I think it's the same thing, right? Yeah, it's the same thing. Okay, so it's this one. So here we have to use Jordan decomposition. Okay. So then because our x naught, did they give us some x naught? Okay, so x naught is 3, 2 here. Oh, okay. So because you can see the x naught, this is from part D lah. Okay. I mean from part 1D, 1D, right? So that means xh is actually given by 1D. So let me just copy and paste this one without solving. Okay, because I believe you have no issue solving this. So this is our XH actually. So let me just underline. This is XH because you got two so-called effects on the response of the system. One is by the initial condition. That is from question 1D. Question 1D. So this is our XH. This is the vector XH of t. Okay? From question 1D. So now we just need to evaluate this guy. Okay? This guy, right? So in this case, our T naught is actually 0. You can see from here. Okay? So our T naught equals to 0. Then, as we have gone through in class, we need to go through computing the 3 steps, or rather 4 steps, right? Okay? But 1D is done, so the computation of the homogeneous solution is not necessary. Okay? But we can write down the e to the at lah. So let me just go through step by step. So this one is okay already. So then we have our step 1. So get e to the at. Get e to the at. This one still must compute. Okay, because you need to compute this second term, the particular integral. So e to the at in this case, right, must be e to the jt. So this is p times e to the jt times p inverse. Okay, but because we already worked out what are the eigenvectors already, or generalized eigenvectors already. So we have 4, 4, and 1, 0. So here will be 4, 4, 1, 0. Then the e to the jt will be e to the 3t. Is it 3 or minus 3? Or minus 3. So this is e to the minus 3t. Then e to the minus 3t. Then this guy is always t e lambda t. So t minus 3t, 0. And then the p inverse you must compute also. So p inverse, right? Can see from here is going to be minus 1/4. Okay, 1 over minus 4, I can see 0 minus 4. Then after that, you take the conjugate, which is 0, 4, and then minus 4, minus 1. Legit, is that right? Can? So now you need to compute this. Okay, we need to compute this. So therefore, this guy will look like, wait, okay, I'll leave the minus 1/4 outside first. Then after that, I compute this, which is giving me just te. Oh, you can see the minus 3t, e to the minus 3t always have, right? So might as well take it out lah. Okay, and you try to simplify as much as you can in the process. Can I factorize out the e minus 3t because all terms in the matrix here, right, got e minus 3t, so can factorize out. Then subsequently, I just have to deal with the so-called coefficients here, right? So which means to say that the first one will be minus 4t. Just check for me. Then the second one will be, wait a minute, is that correct? Yeah, that's correct. So then I have minus 1 plus 4t, minus 1 plus 4t, that's legit. 0 minus 4, that's a minus 4. Finally, this will be a 4. Let me see if this is legit. Yeah, bottom line is 0. No, 0, then this is a minus 4 here. This is a minus 4t, this is minus 1 plus 4, right? Plus 4t, that's correct. Yeah, looks correct. Okay. So then, at this juncture, I think because there are so many 4s here, might as well we just multiply in the minus 1/4. Okay, so that before we multiply this, it will be easier. So here, therefore, your e minus 3t, then you're going to get t. Then there's a minus 1 here, right? So therefore, you have, let me see. So you have 1/4 plus 1/4 minus t. 1/4 minus t, that's correct. Then after that, you have 1 here, and this is also a minus 1. Is that legit? Can Then after that, you multiply by the first matrix. So that will give you e to the minus 3t. So then this will be a 4t. So 4t plus 1. So this guy will be what? 4 times this guy will be 1. 1 minus 4t. 1 minus 4t minus 1. So it's minus 4t. Then the other one will be 4t. 4t, just 4t then. Okay, then the last one will be 1 minus 4t. Is this correct? Correct, ah? Thanks. So this will be e to the at then. Okay? Yeah. So e to the at computed already. Then this is our xh. So xh no need to compute. So the step 2, let me write down. Step 2. So xh already computed. Already done in question 1D. So this one no need to redo. Then the step 3 is the particular integral. So this is the most tedious step. So get xp. Yeah. So the particular integral xp of t is this second term. This is our xp. So therefore, you have to change the t to t minus tau inside your e to the a expression. Okay? So therefore, this will be integral from 0 to t. So this is your e to the at. So you just copy and paste. Okay, maybe let me rewrite. So it'll be e to the minus 3 t minus tau. Okay, you can see this is a t minus tau. Then this is 4t minus tau plus 1 minus 4t minus tau. Then 4t minus tau. Then the last one is 1 minus 4t minus tau. Okay, so basically it's from here. So replace t by t minus tau. Then after that, the excitation. So the excitation is e minus 3t0, right? So then you just plug in e minus 3 tau 0 d tau. Okay, so if you write this down, right, you get quite a bit of marks. If it's okay, let's say if it's a 15-mark question, then you just write this down lah. Never solve, maybe minus 5, I think. That means you still get 10 marks. Is that right? So this is actually simpler than it looks, if you ask me. You know why? Because this is e minus 3 tau. So if this is e minus 3 tau, you multiply to the first term, then it's going to simplify a lot. Okay? So you see, this is going to be equivalent to, right? This turns to only e to the what? E to the minus 3t, right? Because the plus 3 tau cancel with this thing. Can you see? So therefore, it becomes like that. It becomes like the e minus 3t you can factorize out. E minus 3t. Factorize out. Okay, let me just put the cancellation here. So you see, you can cancel this with the minus tau term. Okay, because minus 3 times minus tau is plus 3 tau ma. Then plus 3 tau, this is minus 3 tau. So okay lah, cancel lah. Then you're left with only with the minus 3t term, e minus 3t term. But that one nothing to do with tau, so you just factorize it out. That means this thing become what? This one become 1, 0. So if it's 1, 0, then you multiply by this. So therefore, actually, this one turns out to be quite easy. It's just this times this plus this times this, right? So it's only the first term. I mean, the first column is like that. Any objections? Huh? What yi tau? Oh, sorry, yi tau. Okay, this one I put red color. Is that okay? Yeah, so you see this is e minus 3 tau, right? Correct not? So this is a 0, 0 don't care. So which means actually this one can factorize out. So become 1, 0 times e to the minus 3 tau. Okay, wait. I write one more step because maybe it's not clear. Hold on. Okay, wait, let me write one more step. So you see this is e minus 3 tau. But what is this? This is e to the minus 3 tau times 1, 0. Okay, hold on. Let me just make the e minus 3 tau outside. I mean behind, so it's easier to write. So this is times 1, 0. Correct not? It's like that, right? So then this is a scalar. Then there's another scalar here. What? This e minus 3 times minus tau. Then this is e plus 3 tau. What? So plus 3 tau, this is minus 3 tau. So then cancel. Then you're left with the e minus 3t, nothing to do with tau. So just take it out. So therefore, you multiply to the 1, 0 for the pink matrix. Okay, so this pink matrix multiply to 1, 0. So then you get this matrix here. I mean this vector here, which is just the first column because it's 1, 0, right? Any other questions or objections? Then you see this one like chicken feed to integrate, what? So therefore, let me write. So this will be e minus 3t, just integrate. So this is 4t minus tau plus 1, right? Correct now. So it's basically 4t minus 4 tau. So it become, you can write it as 4t plus 1 tau. 4t plus 1 tau. Because the 4t can put the plus 1 together lah. It's a constant in tau. So you integrate, get just tau. Then minus 4 tau square over 2. So become 2 tau square. Can minus 4 tau integrate. So 4 tau square over 2 so become 2 tau square. Okay, can So then this one the same thing. So it's 4t times tau. Okay, then minus 2 tau square. Same thing. Okay, minus 4 tau. You integrate, get 4 tau square over 2. Can So therefore you must remember to plug in the 0 and t for the limits. So you just compute that, you get the answer already. I mean as in for the particular integral. So this guy will be e to the 3t. So you sub in t, this guy. So it will be 4t plus 1. Let me make it neater. So it will be 4t plus 1 t, then minus 2t square. Minus 2t square, that's correct. So if you sub in 0, you get nothing. Okay? So the second row will be 4 tau, 4t square then. 4t square minus 2t square. So then we just simplify. E minus 3t multiply 2. So this guy looks like what? 4t square minus 2t square. So you're left with 2t square. Then you have plus 1, so plus t then. Okay? Then the second row will be just 2t square. So that's your particular integral. I wonder if the answer is correct. Yeah, sum it to the xh, right? Yeah, so I don't know, let's check. So the final step, the step 4 will be to just write down the answer. So the x of t equals to xh plus xp of t. So you just copy and paste. So this is our xh of t. So this guy will be e to the minus 3t, 4t plus 3, 4t plus 2. Then the xp is right here. So therefore the net result will be e to the minus 3t. They just sum out this part. So it'll be 2t squared plus 5t, right? 2t squared plus 5t plus 3. Is that correct? Then the other one will be 2t squared plus 4t plus 2. Correct? Sorry, your... Oh, you can... yeah, you can just leave it like that. This is okay. Yeah. Personally, what I'll do is that I'll leave the... Step 4, I just write down. Okay, that means I just write down this sentence first. Then after that, this part, right, which is the most tedious, this part, I probably do when I have time. If I don't have time, I just leave it like that. I'll just leave like that. Step 4, yeah. No. If you write this, then you get some marks already. Yeah, can. Yeah. So this one I believe you would have solved it in some earlier part if you get the question. So this part after you solve already, then this part, this is a tedious part. So this part after you solve this part, if you never complete, but then if you write this thing down, I think you will still get a good percentage of the marks without solving for this part. Yeah. Because this one is a 1. If I choose 1 here, right, then I'm going to get like a fraction in the generalized eigenvector, which is actually okay lah. Okay, but sometimes because I cannot foresee ahead, right? So I try to make my path easier by avoiding fractions if possible. So therefore, if I change this to a 4, because the span, if I choose 4 also can, it's still on the span, what? But then I know that if I have a 4 here, right, then I can divide by 4 throughout. So I get x minus y equals to 1, or y equals to x minus 1. So then in this case, I will not have a fraction already. But if I choose this one, this is a one, then I have no choice but to have a 1/4 or minus 1/4, right, in my components. So correct. Correct. I can have a fraction inside. It's fine. It's more tedious probably later on. If it doesn't cancels off, it doesn't cancel off early in the multiplication. Any other clarifications to make? Good. Yeah, so that will be 2C. So 2D, question 3, right, would be where we left off from the lecture slides, because we actually didn't solve any inhomogeneous heat transfer problem, okay, which is actually being shown here. So this one, do I need to do? You just sub in the all other parameter values being 1. So your RP, RA minus RA all 1. Minus 1, 1, 1, minus 1. Then the Q is also given 100. Then the other parameters being 1, M also 1, C also 1. So then the initial conditions are given. So I believe this one you should be able to solve on your own, because all other parameter values being 1, so which means this guy becomes T prime equals to minus 1, 1, 1 minus 1. Then after that, T, the vector, plus, so the excitation will be 100 divided by 1, just 100. Then this is a 0. Like that. Then after that, you got to have the initial condition. So T at T equals to 0 will be 30, 30. Like that. So this one thing easy. Can So this one you DIY. So the next one, mathematical modeling problem. Okay. So beer must be cold. Yes, of course. If it's not cold, not nice. But then there's a study recently that no amount of alcohol. This one actually, reported by I think it's World Health Organization, WHO, that no amount of alcohol is actually safe for your body. Yeah. So it's okay lah. Sacrifice like few years. Huh? Yeah. So just don't drink too much, right? Okay. Per day. Half a carton is what? 6 cans. 12 cans in one setting. I don't know. Yeah, anyway, I have not drank alcohol for some time. Yeah. But if you need your sanity, maybe you need to drink a bit. Huh? Drink what? Or drink math too. Okay, so this is the math modeling problem. Okay, I will just model the thing with you. Then after that, you will solve it on your own. Okay? I think the solution isn't that much of a deal, but I think the modeling I will do it with you. So you see, they say that this can of beer, 350 ml usually, having a temperature of 6 degrees Celsius taken out of the fridge, right? Placed in an empty 5-liter cooler box. So cooler box is like those insulative box where you can keep your cold stuff. So let me just okay. So the 5-liter cooler box, maybe I draw something. Then the can of beer is 6 degrees, right? Then you put inside the cooler box. So you're supposed to model the heat transfer between the cold beer and the air inside the cooler box, and evaluate the temperature functions of time. State your assumptions. You may use the parameters given below. So this is the beer, right? And then what happens is that because when you put the beer inside the cooler box, this beer initially is going to be 6 degrees Celsius. Okay, so this is TB lah. TB, let's call it T beer. Then the air inside is TA. Let's call it just TA. Wait, did I use it? TATB, okay. I use a small b here. So therefore, the cold component is the beer. The hot component is the air. This TA, right, is the hot item. Then, of course, there is going to be heat transfer. So the heat transfer must go from where? Must go from the air to the beer, So heat must go into the beer, right? So therefore, this is the heat transfer Q. Can okay? Correct. Correct. Because the box is insulated, right? So therefore, there you can assume that the heat transfer between the box and the outer surroundings is negligible. So it's a closed system. Can okay? Yeah. So therefore, this Q is going to be equivalent to UA, sorry, the heat transfer coefficient times the effective area multiplied by, this is in this direction. So it must be hot minus cold. So it must be TA minus TB. So therefore now, if you apply the conservation of energy to the air, because the air is going to lose heat. So apply conservation of energy to, to air. So if you apply conservation of energy to air, right, you are going to get Q in, which is 0. Okay, so it's Q in minus Q out equals to MACA TA prime. The same kind of equation that we've been using all this while. So therefore, this Q in minus Q out, so there is no Q in. Then the Q out must be just this UA, TA minus TB. So therefore, you get minus UA, TA minus TB, then equals to the right-hand side. So now it's not the air that is gaining heat, the air that is losing heat. Okay, right? So therefore, if you look at the thing here, right, you isolate your TA. So your TA prime is going to be UA minus UA over MACA, then multiply by TA minus TB. So therefore, I call it minus RA times TA minus TB. So the minus sign is at the air now, which is not the same as the lecture example. Okay? Yes? Yeah, why? Correct. That means because it is cold, then the inside air, right, 35 degrees Celsius is quite hot. I mean, it's warmer than the 6 degrees temperature for the beer. So therefore, the equilibrium temperature will be somewhere in between 35 and 6. Okay? So now if you apply the conservation energy to the beer, right, then you're going to get the same thing, right? Q in minus Q out equals to MBCB TB prime. But because your Q in, right, is this UA, TA minus TB, because the heat transfer from the air to the beer. I mean, Q in here is 0. So therefore, this Q out will be 0. So therefore, you get the corresponding coupled ODE, which is TB prime, equals to minus, or in this case, positive, UA over MBCB times TA minus TB. So which is RB, right? You can call it RB times TA minus TB. So therefore, if you put the two equations into a matrix notation, then you'll get the ODE already. So therefore, you have TA prime TB prime equals to, so you see your minus RA here, right? So this one must be minus RA, then RA, this one will be RB minus RB, then times TATB, and that's it. Okay, because you have no inhomogeneous or external excitation term. So then your initial condition must be TA naught, TB naught. So TA naught is 35 degrees Celsius. Then TB is 6. So this is your IVP in matrix form. So you derive the IVP already. Is that okay? Any questions on the derivation of the model, the mathematical model? Yes. Yeah, for your case, it will be that lah. Because if you don't assume the box is insulated, I mean, it's like a perfect insulation, then you will have heat exchange between the inside of the box and the outside surroundings. So if there's a heat exchange between the two bodies there, then you are going to have to model possibly the outer surroundings. But which is commonly encountered in practical problems. That means you have heat transfer between or amongst, right, multiple bodies. So then your matrix is going to be like a big matrix. But of course, obviously, you're not going to get that because you have no time to handle all the different. I mean, such a big matrix. It's very big. That's why usually we will after. So what happens in the practical engineering scenarios is after they model the thing, right? Then they are going to have a super big matrix equation. Then they will solve numerically using some numerical methods to solve. Because, like as what you have seen in the video that you are tested on in the midterms, the one with the Markov chain, right? Then you have a super big matrix. Then actually there's an eigenvalue. I mean, there's an eigenvector problem, right? Of eigenvalue 1, right? But when you solve, you use brute force, which is actually the real application. You don't solve by really solving for the eigenvalues and eigenvectors analytically because it's not going to be done in within reasonable time. Yeah. Mm. Mm. Yes, because the heat transfer coefficient is the effectiveness of heat transfer between the two bodies. So the U is the same. Okay? So this U will be the same for both bodies. But if you're talking about maybe between these two bodies, then like what Naya mentioned, right? If you have a heat transfer between the box and the outer surroundings, then there is another heat transfer coefficient between the box and the surroundings. So between these two bodies, the U is the same. The A is also the same because the A is also the area of heat transfer between that two bodies. Then I will have to mention this A already. Okay, because the masses are like, for example, if you look at the parameters given here, right? They give you the density. They give you they did not give you the mass of the air and the beer, but you can calculate. But you have to like calculate in a smart fashion, So I'm going to mention about the RARB now, because if not, then you cannot get the answers given. Okay, so if you look at RA, right, is UA over MACA. Okay, so RA equals to UA over MACA. CA is no problem, right? Heat capacity of the air, no problem. It's 1,000. But this MA, you have to be careful. So where MA must be the density of the beer multiplied by the volume of the, must be the density of the air. So it must be rho air multiplied by the volume of the air. Okay, volume of air. So density is just 1.2 kg per meter cube. But then the volume, this one by right, the volume is, you have to take the volume of the cooler box minus the volume of the beer. Agree or not? Because that is the remaining volume of the air, Can So, but then the cooler box, you can see that they only give you the height and diameter of the beer can, which means that you can calculate the volume of the beer can. Then this cooler box, you have to take it to be 5 liter. Can, right? So therefore, it must be 1.2, right? Multiplied by the, let me write, volume of box minus volume of beer. The 350 ml, 350 ml is not wrong, but 350 ml is the beer inside. That one is this one 350 milliliter is actually the beer that is inside the can. So actually, more accurately, it should be this, the volume of the beer can, by right lah. So therefore, you have to make a bit of a calculation here. Of course, if you take 5 liter minus 350 ml, also not wrong lah, because engineers usually we estimate a lot. Okay, also not wrong, seriously. Yeah, correct. Volume of the beer can, you're right. Yeah, that's a good point. Volume of the beer can. 5 liters. So now let's put it in numbers. So it's 1.2, the density, multiply the 5 liters, right? So in this case, we convert to meter cube lah. Okay, we convert to meter cube because this one is kg per meter cube So therefore, it must be 5 liters, right? Multiply by a conversion. So multiply by, so 1 liter is what? Should be times 0. Wait, 1 liter is 1,000 ml. So 1 liter is 1,000 ml, right? ml is someone convert for me. Liter to meter cube. I think it's times 10 to the power of minus 6. 0.001 0.001 meter cube Okay, so it's 10 to the power of minus 3 then. Okay, then this is minus the volume of the beer can, right? So this one must be pi times the diameter of the beer can, which is 6.6 cm. So it must be pi d squared over 4. So therefore, it will be pi times 6.6 cm, right? Which is 0.066 square over 4 multiplied by 0.122. Is that right? So this one you can go and calculate, or just leave it like that. Okay, so this will be your MA, because pi d square over 4, okay, times the height of the beer can. Can then actually the A is also a concern. U, this one is straightforward. Okay, U is what did I give? U is 5. So this U is 5. Then MA you calculate. CA is just 1000. Then the area. So what's the area? The area of heat transfer is actually the area that is exposed to the air. So the area that is in contact with the base of the base of the can, right, that is in contact with the cooler box, the one you neglect. You have to minus away. Okay? If you want to be as accurate as possible. So therefore, the area here, right, must be, wait, let me draw the beer can. So the area here will be this top area plus the side area. Okay? So therefore, you have to have pi d squared over 4. So it must be pi d squared over 4 again. This guy, the top area, plus 2 pi RL or pi dl. So it must be pi times 0. So this is a plus 0.066 pi d times L, 0.122. Then this one you calculate. Okay? So this is not exposed to air. Okay? So not exposed to air, you cannot add or else you will have like 2 pi d squared over 4 here. Yeah. Yes. The bottom surface of the beer. Okay, so of course we are making an assumption that because the aluminum is a very good conductor, aluminum can is usually a very good conductor. So then, and the aluminum is very thin, right? Aluminum can usually the material is very thin. So therefore, the temperature of the beer inside is the same as the temperature of the can surface. So that's an assumption that we will make Okay, or else you need to model the heat transfer between the beer can aluminum and the beer inside, which is a conduction problem. Yeah, you're not adding, but you're adding the top. What? This is the top, then this is the side. What? No, this is the area. I'm talking about the surface area that is exposed to the hot air. You see, the air is all over, right? Correct not? So the air is in contact with this area. So this is this. Then the second term, right, is the side. Is the periphery. So the bottom is not in contact with the air. So therefore, you cannot add, you cannot times 2 here. Because some students would think that, oh, that is also part of the surface. So you times 2. Then you get slightly off answers as compared to the one that I gave you. Any other questions? Kara? Okay. So the reality is when you model real world systems, all these are practical considerations that you have to think through. Okay. Or else they are going to, if the effect is huge, it's large, right? Then it's going to affect your accuracy of the answers. Yes. Of course. Yeah, it's but the area of the cylinder is, you have to take this thing times 2, what? Then minus, plus the periphery, plus the circumferential area. Then you minus away. But then when you do that, we might as well just multiply 1. Here, don't multiply 2. It's not volume. You cannot take volume minus area. No such thing. Can Okay, I think I've gone through the necessary intricacies of this problem already. Okay? Then I think the rest I'll leave you to DIY to solve. Because this one not Duhamel, so I'm just using the standard solution. Which one? Yeah lah, 2 pi RH is pi dh, what? This is pi dh, what? The periphery is pi dh. Circumferential area is pi dh. Or 2 pi RH is the same. Can? Okay, good. Okay, so I actually want to talk about this thing lah. Evaluate and comment on the steady state temperature of the beer and air inside the cooler box. Because this one a bit suspicious, because you can see that the steady state temperature is 6.1 degrees Celsius after you have solved for the solution. Okay, so this 6.1 definitely, do you think is what you experience? Let's say the 5-liter cooler box, right? You put 1 can of beer 6 degrees inside. The steady state temperature is 6.1, you know. The beer got so cold, man. No, right? So what is the problem here? What do you think is the problem? This one is like too low. Doesn't meet the expectations, or doesn't meet the experience of our daily, doesn't meet our experience. If you have put some cold products in a cooler box, let's say for barbecue or what, right? You know that it's not going to remain at that temperature. You usually want to include some ice packs, or else it gets warm up too fast. So what is the problem here? This one probably too low. Why? Outside air already 35 degrees Celsius, right? Doesn't quite agree with experience. What material? The beer can? No. No, that means when I take out the beer from the fridge, right, it's 6 degrees Celsius. That one okay. That one just take out 6 degrees, then put inside the cooler box, then close it. Then we are expecting that the long-term temperature, steady state, is 6.1. Oh. That means only raised by 0.1 degrees Celsius for the beer can. It means the beer can, after, let's say, for example, say 6 hours, it's still very cold. Sorry? Never what? Never declare ice cube. Okay. Naya has a valid point, right? That is right. The insulation that in real life, the cooler box is not that well insulated. The cooler box, because we are assuming perfect insulation here, no, between the cooler box and the surroundings. So therefore, in practice, right, in reality, there's no such thing as perfect insulation. So heat will still continue to go into the cooler box and then go into the beer. So actually the beer will get heated up more. Okay? So one reason, there are multiple reasons. So one reason is imperfect insulation between box and outer surroundings, outer environment. Yeah. Yeah, correct. But I say it's too low. So it doesn't agree with our experience. Probably it's not going to be 6, right? It's going to be, I don't know, like 15. It means after some time, the beer, right, actually not 6 already. It's 15 degrees Celsius, not so cold already. Correct. So I'm trying to say that this is too low. So in reality, right, we have imperfect insulation. This is too low, right? So in reality, we have a higher temperature, a higher TSS due to, okay, the first one is imperfect insulation between the box and the outer environment. Okay, so much so that, of course, the hot outer environment, right, will heat up the box air, the air inside the box. Then after that, in turn, heat up the beer. That's one. But there is actually another one that is dominant. Even though the box is imperfect insulation, but you must agree that actually the box insulation is quite good. Okay, but there is a dominant one that is causing the heating up of the beer can, of the beer. You notice, right, when you put inside, right, the cooler box, right, then you open, the can outside has what? Condensation. How to condense? How does the water vapor, which is at a higher energy level in the air, right, condense into water droplet? The energy from the water vapor in vapor form must get removed, right? Where is it being removed? Into the beer, into the cold beer. So there's condensation, right? So that means that actually the beer gain what we call latent heat from the air, from the water vapor in the air. So therefore, actually the heat that is being transferred into the beer is more because there's latent heat gain. Okay, so in reality, we have condensation of water vapor in the air transfers heat to the beer. Okay, good point. The thing is, heat capacity stays quite constant. There will be changes lah. I mean, dependent on the humidity, right, of the air. If the humidity changes, then the heat capacity changes as well. Okay, but it remains roughly constant. Okay, unless your humidity or your pressure, right, changes a lot, then the heat capacity will change a lot. Okay, but this one I think negligible lah. The change in the heat capacity typically not being modeled that accurately unless your temperature change is like very huge or pressure change is very huge. Okay, yeah. So predominantly, I think it's the condensation effect. Okay, there could be another one that is the heat conduction from the can to the box. That one also not being considered. Okay, so heat is also conducted to the beer from the box. Okay, at the base of the can. Okay, but that one you never model what? It's between the beer and the box. It's not between the beer and the air. Any questions? Good. Okay, if no, I think we take a short break. Then I'll do the modeling of questions 5 with you. Okay, and probably that would complete this tutorial session. Okay, so this question 6, I think we will come back and attempt after topic 7. Yeah, because this part we have not covered in topic 7 yet. Okay, then question 7 is very tedious, so just not optional, right? Because you can see the eigenvectors here are complex eigenvectors. Okay, so this one won't be tested, right? That's why I put optional, right? Not tested. Maybe I put here optional, so this one not tested. Else I think too tedious, not enough time. So let's take a short break. Okay, so as I was saying, right, you will be getting a past year finals to practice by end of this week, like by Friday. Okay, I'll upload to the X site without any solutions. You try first. You must try. Okay. Then after that, I will upload the solutions next week. Probably I'll give you 1 week to try. So maybe next Friday. Wait, next Friday a bit late. Okay, maybe next Wednesday. Next Wednesday I'll upload the solutions. Okay, but you must try first, please. Okay, the format will be exactly the same as this year. Can so you'll be MCQ, something like your midterms are like MCQ question 1, then question 2 and 3 will be structured, then 2 ABCD, 3 ABCD, that kind of thing. Okay. So question 5. Last question for today, for this tutorial. I think you should have seen something like that before in your circuit analysis, your circuit theory. So this is chicken feed, right? Kind of. Right. So this circuit, usually for circuit analysis, typically we will not apply conservation of energy, but or of course momentum. There's nothing moving in this problem. But typically what we'll apply, right, is the conservation of charge, which is actually your Kirchhoff's current law. And along the way also your Kirchhoff's voltage law. Okay. So this one is application of KVL and KCL lah, right? And then maybe just a recap from your circuit theory. In order to apply KCL, KVL, typically you will need to choose loops, right? You need to write down the voltage increases as well as decreases over any loop, okay, a closed loop. So therefore, I am going to just choose 2 convenient loops. Actually, there's no straight and fast rule on which loops you choose. Okay, I'll just choose the simpler loops such that I have less work to do. So what's the objective? The objective is to derive the equations involving I1 and I2, because that's what you're trying to find. Okay, the currents I1 and I2, that's the objective. So therefore, you should try to involve I1 and I2, but preferably kind of as separately as possible. Okay, what do I mean by that? Because you do not want to have coupled equations if possible. Okay, but if not possible, then you will have coupled equations. So what I'm trying to say here is this. You can see that there's I1 here. I1 is actually flowing into this R1. So therefore, I will just make this first loop and apply KVL. So I call this loop 1. Okay, so apply Kirchhoff voltage law over loop 1. Okay, so you can start at anywhere. I'm going to start at this point. I just start point. Okay, so I come back to the same point. Then I go through resistance R1. Oh, by the way, you guys may have learned a different way of applying KVL. Okay, but I'll just apply it like that. You can apply in your own way, doesn't matter. Right? So resistance is going to decrease your potential difference. So therefore, you have a negative. Okay, so minus I1 R1, because there's a voltage drop across resistor R1. Then after that, passes through this inductor. So therefore, it will be a minus L1 I1 prime. Okay, inductance multiplied by the rate of change of I1, that's going to cause this voltage drop. Then after that, flow through this junction. But you have to be careful. When you flow through this junction, what is the current flowing through R2? It's going to be I1 minus I2, because flow out. So this part got to be I1 minus I2. So I1 minus I2 is flowing through R2, right? So drop another voltage, which is I1 minus I2 times R2. So after that, go back to the original start point, equals to 0. Any objections? Can? Okay, so certainly I'm going to rewrite this ODE with I1 prime as my isolated term, because I'm going to write down I prime equals to AI, right? Eventually. So therefore, I'll isolate I1 prime. Then I have a 1 over L1. Then multiply by what? So I'm going to have multiplying by minus R1 multiplied by I1. Then I have this is minus, hold on. Apologies. So let me just put the I1 together. So you can see there's a minus I1 here, and then there is a minus I1 here as well. So that means it's going to give me minus R1 plus R2 times I1. Okay? Then after that, I'm going to have a plus R2 times I2. So that will be my equation 1. So this one I put row 1. Okay, now I just leave it as is. Okay, so you can see I1 prime depends on both I1 and I2. So that's coupled. So obviously you need another ODE involving I2 prime. Can? So therefore there is another loop 2. Okay, some of you may choose this loop. Is choosing this loop okay or not? Actually okay also, right? But there is another loop. There is this bigger loop. This is also another loop. Okay, you can go past R1, L1, then after that go past L2 here. Okay, but you see, the prime term appears at the inductors L1 and L2. So certainly you wouldn't want to have I1 prime and I2 prime in one ODE. Okay, because if you have, then what you will need to do is to substitute one of the prime terms into the other equation to simplify. Or else you cannot put in the prime like I prime equals to AI, that kind of ODE. Okay, that kind of system. So therefore, we should try to avoid the two primes in one equation. So therefore, I'm not going to pass through L1. Okay, just now pass through already. So now I pass through L2 without passing through L1. So the second loop will be something like that. So this is loop 2. Okay, So now we apply KVL over loop 2. So I start from the battery, which is the voltage source E of t. So this one I start here. Okay. So therefore I'm going to have E of t, and that's a positive. So then after that, I pass through R2. Be very careful. I pass through R2. The current is now I2 minus I1. The current, this one is I1 minus I2, right? So if you go in the reverse direction, it must be I2 minus I1. You have to reverse it. Can? So this one will be I2 minus I1. So you have a voltage drop of R2 multiplied by I2 minus I1. Okay, it must be consistent. If you show this direction as I1 minus I2, the opposite must be I2 minus I1. Can? So then after that, you are flowing through L2 because this one got nothing. Okay, R2 here, then after that here, pass through L2. So minus. So your I2 is passing through L2. So therefore, it must be L2 times I2 prime. Then after that, you go back to the battery. So it goes to 0. Any objections? I2 prime because it is passing through the inductor. Inductor, the impedance or the resistance, right, is the voltage drop is caused by L2, the inductance, multiplied by the rate of change of the current. Because if the current is a DC current and not changing, then of course there's no voltage drop because the inductor is just a coil of wire. Can? Okay, so if you look at this equation and you rewrite it in terms of isolating I2 prime, then you're going to get 1 over L2 multiplied by, wait, let me see what's this. Okay, multiply by, so it's going to be R2 times I1. Then you have a minus R2 times I2, then plus E of t. Plus E of t divided by L2. Okay? Minus. Why? Because this thing bring across. So this one will remain as positive. Okay? So you can see that there are two equations here. So if you combine the two equations, then you are going to get your system. So your system is going to be I1 prime, I2 prime, and that's equivalent to a matrix multiplied by I1, I2, plus a E of t term. So you have a E of t over L2 at the second equation. Then a 0 at the first equation, no excitation. So this part, right, you just have to put it down accordingly. So this one will be minus R1 minus R2 over L1. Then this is R2 over L1. Yep. So this is your system of ODEs. Because this is I2, what? Hold on. The second equation I put at the bottom. So then the top one is the green first equation. Any other questions? You have no questions, then the IVP, which is for part 2, you just sub in the values, right? And then the initial condition is that because the switch is open for a long time and closed at t equals to 0. So therefore, there's no current flowing inside the circuit. So therefore, you get 0, 0 as your initial condition. Okay, so I'll leave you to do part B and C on your own then. This one nothing much, just sub in values only. Then write down the initial condition. Then part C also just solve using Duhamels. So let me mark attendance. So we finished tutorial 6, and later on during the lecture we will continue with topic 7. Alexander, Aliyah, Emelina, Angelico, Jiashon, Brian, Chen Chang, Zhen Yi, Ivan, Yang Diang, Emilia, Erwin, Yanjin, Zhanyang, Dongbing, Noritetsu, Javier, Zoe, Jordan, Kayla, Kevin, Ken Leong. Okay. Wait, let me see. Ken Leong. Okay, I'll mark yours first. Charan, Dawson, here. Chen Ying, Jonathan, Kun Yong, Mac, Nikhil, Mohan, Azari, Danish, Irfan, Naya is here. Bing Jie, Peng Hong, Zixuan, Fadila, Phoebe, Yan Heng, Sherwin, Benjamin, Raymond, Reese, Rujira, Junpang. No. Jerome, no. Sean Bryan, no. Justin, Hao Po, Ryan, Sohadi, Johans, Wei Yan, Yi Zhong, Tianzhen, Trisha, Yang Hong, Zhi Kang, Xing Zhi, Zotet, Zumpin Y. Okay. Okay, you can go and there'll be another class for the later second class. So I'll see you later on at 2 for the lecture.